linear subspaces. Let V plus F dot be a given linear space. Here V is a non-empty set, plus is addition of elements in V, F is a field, and dot is scalar multiplication of field elements by elements of V. Let S be a non-empty subset of V. The structure consisting of S plus F dot is said to be a subspace of the given linear space if and only if the structure with S is a vector space itself. Examples. Each of the following structures are subspaces of R3 plus R dot. Here plus is the usual addition of elements in R3, and dot is the usual scalar multiplication of vectors in R3 by real constants. A. S plus R, where S is the set consisting of triples x, y, z, such that x plus y plus z equals 0. In order to establish that the structure with S is a subspace of R3, we will need to verify that the structure with S is itself a linear space. That is, we need to verify all properties of a linear space are satisfied by the structure with S. I'm displaying here the various properties that would need to be verified. Now, what is S? The set S consists of triples x, y, z, such that x plus y plus z equals 0. Now, the structure we are studying right now, S, addition of elements in R3, the field of real numbers, and scalar multiplication of real numbers by elements of R3. Now, first thing we need to ensure is that this operation is a binary operation on S. In other words, we need to show that S is closed under addition. If you have two elements of S, their sum is still in S. But not only that, we know that dot is a scalar product of real numbers by elements of R3. But do we know the same thing holds for elements of S? That needs to be confirmed. So we need this property. We can call it closure of scalar multiplication. Okay, so let's confirm that right now. So let A be a real number and U be an element of S. Here's what we're asking. Is the scalar product, so is the scalar product A dot U in S? We need to confirm that it is. Okay, so let's see. Let's find out what AU is. A dot U by definition, is going to be the product of A times the first entry of U, A times the second entry of U, A times the third entry of U. Now, let's specify U. Let's say U equals U1, U2, U3. Okay, in that case, then A dot U becomes AU1, AU2, AU3. Now, if you are asking this question, is this result in S, then you're asking, is it true that when you add the entries, you get 0? Well, let's see. We know that AU1 plus AU2 plus AU3 is the same as, if you factor out A times U1 plus U2 plus U3. But remember that we picked U to be in S. So that means when you add U1 plus U2 plus U3, you get 0 because U belongs to S. If this is a vector in S, its entries must satisfy the conditions for entries in S, for elements in S. So the sum of U1 plus U2 and U3 is 0. So you get A times 0. So that's 0. So we conclude that the dot product, the scalar product, A dot U, does happen to belong to S. Why? Because the entries of that vector satisfy the conditions of entries that belong to S. The sum of the entries was equal to 0, so this vector belongs to set S. Okay, now another thing we need to check is that addition of elements in S is closed. So let's work that out next. So let U1 and U2, let's try something different. Let U and V be elements of S. We want to show that the sum of U and V also is in S. So let U, V belong to S. Now, let's specify what that means. So, if we set U to be U1, U2, U3, and V, we set it to be V1, V2, V3. Individually, when we add U1 plus U2 plus U3, we get 0. Also, when we add V1 plus V2 plus V3, we get 0. That's what we know. If we take U and V to be elements of S, we know that much. Now the question we're asking right now is, when you add them up, do you still get the result is also in S? So let's do the addition right now. So you have U plus V equals. Now we know how to add elements in R3. You add entry by entry correspondingly. U1 plus V1, U2 plus V2, and U3 plus V3. Now we're asking, is this an element of S? In other words, we're asking, if we add these three entries, do we get 0? Well, let's see, let's add these three entries. So we're adding u1 plus u2. Excuse me, I have to make a correction here. u1 plus v1. This is supposed to be u1 plus v1 here. Okay, so we're adding this entry, u1 plus v1, plus this other entry, u2 plus v2, plus this last entry, u3 plus v3. Now, observe that this is addition of real numbers, so we can rearrange these terms. I can rearrange u1 plus u2 plus u3 plus v1 plus v2 plus v3. Now observe that's 0 because u is in S. That second group is also 0 because v is in S. So we have succeeded at establishing that u plus v is also in S. Okay, now next set of properties we want to establish are the associative property and the commutative property. Now let's observe the following. If I picked elements that belong to this set S, since S is a subset of R3, then I just picked elements that are in R3. So let U, V, W belong to S. Since S is a subset of R3, then we conclude that U, V, W are elements of R3. Oh, so then it follows, since R3 is a vector space, that those elements obey the associative property under addition. Similarly, for the commutative property, if I picked let U, V be elements of S, well, since S is a subset of R3, then U, V are elements of R3. It follows that the commutative property holds because R3 is a vector space. Notice that what we are experiencing here is that these two properties have been inherited from the given vector space, R3. That happens with those properties in some other properties. Now, let's observe that we need to, in order to establish that S, the structure with S is a vector space, it needs to contain the 0 element, and for every element in S, its opposite must also be in S. Notice that we have to check this because some subsets, if you give me a set that contains theta, and then you give me another subset, and then you give me a subset of that set, there is no guarantee that that subset will also contain theta. So we have to find out whether theta belongs to S. So does theta belong to, so does theta, which is 0, 0, 0, belong to our set S? Well, the question we have to ask is, if we add the entries, do we get 0? If that's the case, then that element belongs to S. Oh, well, in this case, that's pretty much true. I'm adding the 3 entries of theta. The answer is 0. Therefore, let me write it in words. Therefore, it does belong to S. Theta does belong to S because when you add the entries of theta, you do get the condition of S is satisfied. The condition of S is that adding the entries gives the result 0. Okay, now, so now let's verify that when we pick an element of S, the negative of it is also in S. Once again, this property has to be confirmed, because if I have a set, in this case R3, and I take a subset of that of it, the subset may not satisfy this condition. So is it satisfied by our current set S? Okay, so let U belong to S. Okay, so if you tell me U belongs to S, then the sum of its entries equals 0. Now, what's negative U? We know that negative U is simply the scalar product negative 1 times U. But that's just negative U1, negative U2, negative U3. Now, the question we're asking is this entry also in S? In other words, if I add these three entries, do I get 0? Let's find out. Let's add them together. So let's take negative U1 plus negative U2 plus negative U3. Now, here is a negative sign. This is an addition of real numbers, so I can factor out the negative sign. But I know that U1 plus U2 plus U3 equals 0. So I end up with negative 0. Well, negative 0 is just 0. Okay, so confirmed. For this set S, whenever there is an element U in S, its opposite is also in S. Okay, last four properties of linear spaces. We need to verify that if A is a real number, UV are elements in S, distribution of scalar multiplication over vector addition is satisfied. If A and B are real numbers and U is an element of S, distribution of scalar multiplication over field addition is satisfied. If A, B are real numbers and U is an element of S, the field multiplication and the scalar multiplication obey an associative property. And finally, if U is an element of S, the scalar product of the multiplicative identity of R and U is equal to U. Now, here the properties, all these four properties are inherited from the vector space, from the linear space R3. How is that? Well, if I pick two elements in S, since S is a subset of R3, then these two elements are in R3. So this is immediately obtained because that property is satisfied in R3. Similarly for the last three properties. Okay, so let's look at the second example here. So here's what we need to be thinking about. When we are asked to establish a structure is a subspace of a given linear space, we're having to verify certain properties with respect to the set, but we are not going to need to verify those properties that are inherited from the given linear space. Now here in B, S is the set consisting of all x, y, z such that x equals to 0. Now let's draw a picture of this and then realize that that's just similar to an example we previously considered. So here is the XYZ space. Now, if you tell me S is the set of all triples XYZ such that X is 0, that means you're talking about the YZ plane. Now, an earlier example in a separate video, we studied a similar situation, but we were not looking at the YZ plane. We were looking at the XY plane, and we established in similar fashion as we did in part A that the structure happens to be a linear space. The way we did that is we verified closure of the scalar multiplication, closure of the addition, we inherited the associative property, we inherited the commutative property, we had to check that the set contains theta. In this case, it's easy to confirm. That's the origin. The YZ plane contains the origin, so that's not difficult to verify in this case, but it needs to be verified. Also, we confirmed in that previous example that whenever you have an element in the set S, the opposite of that is also in S. So I'm referring the audience to see that example. And then the last four properties were inherited from the linear space R3. Okay, let's look at another example. The structure consisting of Pn plus R dot. Here Pn is the set of all polynomials of degree n or less, plus is the usual addition of functions, and dot is the usual scalar multiplication of constants by functions. Now that structure is a subspace of the space of continuous functions on the set of real numbers. Okay, so what do we need to know? We need to begin with our hypothesis that the set of continuous functions is a linear space. So let me go here. So this is my given information. So that's a linear space. Now, here's what we're being asked to show. Show the set of polynomials of degree n or less is a linear subspace, or simply a subspace of that space of continuous functions on R. Okay, so let's see. I will need to verify that scalar multiplication is closed. So let let me call this the subspace properties. I don't have to check every single linear space property. I just need to check the subspace properties. And I'm going to list them here. Closure of scalar multiplication, closure of Pn under addition, containment, and let me see if I can say this better. Containment of the additive identity, in this case theta of x equals 0. That will be the identity element. So we need to show that the set of polynomials contains that element. Well, that's not going to be difficult. This is the 0 polynomial, so it's an easy check. The function theta of x equals 0 is a polynomial of degree 0. It's a constant function. And then containment of additive inverses. So containment of additive inverses. And here what we're thinking is, if you have a polynomial, is there another polynomial such that when you add them together they cancel out and give you 0? The answer is also, it is simple to come up with that polynomial. Just put a minus in front of every term and that will follow. Okay, let's talk about, let's go back. So these are the only things we need to check. We don't need to check anything else because it will be inherited from the given linear space. So closure of scalar multiplication. So let A be a real number. So I'm picking a field element. And let P of x equal an xn plus plus a1x plus a0. Notice that this could be an n-degree polynomial, or it could be a polynomial of less than degree n, and that will happen if an is actually 0. So this is the generic element in Pn. So this is a generic element of Pn. Now, what's the scalar product of A and the polynomial? Well, it's the usual one. AP of x, you distribute, you get the constant A times an xn plus plus the constant A times a1x plus the constant A times a0. Observe that that's still a polynomial of degree n or possibly less. So it does belong to the space Pn. Okay, so scalar multiplication, closure of scalar multiplication holds. Now, clearly, closure of addition of polynomials of degree n or less holds. I'm going to erase because I need this space to do the algebra. So let's pick two elements in Pn. So let P of x equal to anxn plus plus a1x plus a0. Q of x, another polynomial, bnxn plus plus b1x plus b0. So each of these are polynomials of degree n or less. Now, if we add them, notice that we also get a polynomial of degree n or less. Here let's combine like terms. So this will be an plus bn xn plus plus a1 plus b1 x plus a0 plus b0. Okay, so this happens to be a polynomial of degree n or less. So closure of Pn under addition holds. Once again, the function theta of x equals 0 is a polynomial of degree 0. It's a constant function. It's a polynomial in its degree 0. So checked. Pn contains this, the set of polynomials degree n or less contains that function. And that's the additive identity. If I take 0 and add it to a polynomial of degree n or less, I'm just going to get that polynomial. Okay, let's do this one. Containment of the additive inverses. So I'm going to begin with a polynomial in Pn, and I'm going to show that there is another polynomial of degree n or less that will cancel it when they're added together. Okay, so here we go. Let P of x equal to an x to the an x to the n plus plus a1x plus a0. So negative P of x, which will be negative a n x to the power n. Sorry, this is supposed to be n exponent. I'm doing this backwards. That's supposed to be a subscript, an, and that's supposed to be a power. So an xn plus, and so on. Everything else is fine. So this will be plus negative an minus 1 x to the n minus 1. So I'm going to put a minus there to indicate that that's not what's going on. Okay, now observe that if you add this together, P of x plus negative P of x, everything cancels. So you get 0, so confirmed. How do I know I've confirmed? I created another polynomial that's also of degree n or less, that when you add it to the original polynomial, you get the additive identity. Okay, there are more examples we have to look at. Third example, determine whether the given structure is a subspace of R3. A, let's call this A. The structure S with addition of elements in R3, the field of real numbers, scalar multiplication of real numbers by elements of R3. In AS is the set of all triples XYZ such that x squared plus y squared plus z squared is less than or equal to 1. If you think about that description, if you think long enough about that description, you will realize that there happens to be a solid sphere of radius 1 center at the origin in the three-dimensional space. So the question seems to be very difficult in that it is asking you, so is that structure a linear space or not? So if it is, if the answer is going to be affirmative, then you have to verify the subspace properties, the four subspace properties. If it isn't, then you're going to have to display which of those four subspace properties is not satisfied. So let's go here. So I have S. So here is the XYZ space, and that's just the solid ball. I call this a sphere, but it's actually a ball. It's a solid ball. It's everything, the shell and the inside of the ball or sphere that is centered at the origin and has a radius 1. Now let me pay attention to this point right here. That's the point 1, 0, 0. Now that is an element of S. So 1, 0, 0 belongs to S. Why? Because 1 squared plus 0 squared plus 0 squared is 1, which is in fact less than or equal to 1. I'm suspecting that my property of closure under addition is not going to be satisfied. I won't bother checking anything other than this right here. I suspect that this S, the structure with this set, is not a linear space. It's not a subspace of R3. It's not a linear space because it doesn't satisfy closure of addition. Let me call this U. So if I add U plus U, what do I get? Well, I'm going to get 2, 0, 0. Sorry, that does not belong to S because it doesn't satisfy the condition of being in S. If you take 2 squared plus 0 squared plus 0 squared, that equals to 4, which is not less than or equal to 1. Okay, so we conclude that the structure S plus R dot is not a subspace of R3. Because one of the subspace properties is not satisfied. Okay, another one, the structure S plus R dot, where S consists of triples XYZ such that the product XYZ is greater than 0. Okay, I can say that I can immediately see that this is not a subspace. Just think about which of the subspace properties cannot be satisfied. Let me erase so we can write our set S. The description is S consists of all triples X, Y, Z such that the product XYZ is greater than 0. Let's double check on that. Greater than 0. Okay, so here's the problem. These are, I'm displaying right now my subspace properties, the ones that I will need to verify. There is one of them that is clearly never going to be satisfied. It cannot be satisfied. that S contains theta cannot be satisfied because theta would be 0, 0, 0. When you multiply 0 times 0 times 0, you're not going to get this condition satisfied. Okay, so just with that, I know that the structure S plus real numbers dot is not a subspace of R3. Because theta, which equals 0, 0, 0, is not an element of S. Okay, so there we have it. Some examples. So we have our definition of what a linear subspace is, and we have various examples. Let's remark that in establishing that a structure S plus F dot is a linear subspace of a known linear space V, with S not equal to the empty set and S is subset of V, we find that various properties hold because they are already verified for the vectors for the linear space with set V. Consequently, to establish that the structure S plus F dot is a subspace, it suffices to check 3 of the linear space axioms. Which are the 3? And you might remember that in our discussion we have checked 4. So we checked the closure of scalar multiplication, closure of addition, the containment of the additive identity, and the containment of additive inverses. These are 4 properties. Our notes are telling us that there are 3 properties. Well, let's investigate why that's the case. Notice that in this first property, the closure under scalar multiplication and the closure of addition tells you the following. The closure of scalar multiplication will say that -1 dot u is in S. The closure of addition will tell you that if you take this guy and you add it to u, that belongs to S. But who is this? When you do the algebra, you will end up concluding that this is just theta. So I could avoid, if I verify these 2 properties, I can avoid having to verify that S contains theta. Oh, but furthermore than that, I could also avoid checking that if u is in S, negative u also is in S, because once again, this closure, if you pick A to be -1, already gives you that result. So it looks like it's not 3 but 2 properties that need to be verified. So let me put this away. When you are verifying a certain structure is a subspace of a given linear space, check 2 things. Check closure of scalar multiplication and a closure of under addition. Okay, so that will be our theorem for this lesson. Let V plus F dot be a linear space and let S be a non-empty subset of V. If 1, for each uv in S, u plus v is in S. 2, for each A in the field and u in the space S, in the set S, the scalar product A dot u is in S. So if you get these 2 properties satisfied, then you get that the structure S is a linear space. Consequently, S is a linear subspace of the given vector space, of the given linear space. Okay, so I'm going to quickly here run through the proof. The proof, if you tell me that the structure with S is a linear space, you are telling me that all properties of linear spaces are satisfied. As you can see, the only ones that we end up checking, the only ones that end up mattering are these two. Everything else is inherited. In checking one of the properties that if U belongs to S, then the additive inverse is contained, we have to use a certain fact that when you're taking the scalar product of 0 and U, you get theta. That will require a verification that is being left as an exercise for the reader, for the audience. Okay, very long video, but that's all for now. Thank you for watching.